Okay, so continuing on, if you remember earlier, we talked about the sine of 45 degrees and the cosine of 45 degrees. And these two were equal to one another. And it equaled 1 over the square root of 2, if you remember correctly. Well, because of that, any triangle with a 45-degree angle has sides that are proportional. So earlier, we talked about the 45, 45, 90 triangle with the unit circle. And we said that we knew the radius was 1, and so this was going to be, these two sides were going to be the same, because these two sides here were going to be the same because this was an isosceles triangle, and we found this side to be 1 over the square root of 2 and this side to be 1 over the square root of 2. Now, we have something in math, and what we're doing with this particular section is called reference triangles. And with this reference triangle that we're going to use for 45, 45, 90, we simplify what I gave you earlier. Okay? We're going to simplify it. Because notice that 1 over the square root of 2 is kind of difficult to remember. So if we multiply all these sides by the square root of 2, by the same scalar, 1 times the square root of 2 is the square root of 2. And 1 over the square root of 2 times the square root of 2 is 1. And since these sides are the same, that's going to be 1. Now, believe it or not, even though these look different, this is the same because of how these sides are proportional. Okay? This is the one that we are going to use as our reference triangle. And I'll abbreviate the word triangle with a triangle. This is a reference triangle. Okay? Now, the same thing occurs with sine and cosine of 30 degrees. Okay? So 30 and 60 degrees are the tricky ones. If you remember earlier, we said that we had the earlier I drew us the 30-degree angle. So we knew that was 60, and we said that this was 1. The short side was half of the hypotenuse, and the long side was the square root of 3 times the hypotenuse, times the short side, excuse me. Well, that's what we used earlier. Now, the reference triangle for 30, 60, 90 is going to be just a little different, just like our last one, okay, where we multiplied through by the common denominator of a square root of 2 up top. We're going to multiply through by 2 here as the common denominator. So that's going to give us 2, 1, square root of 3. 2, 1, square root of 3. So our 30-degree side, or the long side, will always be square root of 3. Our 60-degree side, or the short side, will always be 1, and our hypotenuse will be 2. Now these are the reference triangles for 45 degrees and 30, 60, and 90 degrees, okay? So these are the ones we are going to use as we get ready to do reference triangles. All right, so how do we find a reference triangle? Well, let's suppose for a second that you have some angle, okay, that you have some angle drawn here, and let's make it viewable. And this angle that's right here, this is going to be alpha. Excuse me, not alpha, theta. That's going to be angle theta. So if we are going to if we're going to find a reference triangle, here's what we have to do. We drop a perpendicular from some point. This point is going to be AB. From some point AB to the horizontal axis. Okay? What this is going to do, that perpendicular is going to make this a right triangle. Now, this is our reference triangle. Now the angle in here, this angle right here, alpha, is our reference angle. Okay? It is our reference angle and will always be positive, taken in a positive form. Okay? So, for instance, let's sketch some reference triangles and their angles. Okay? So we have, let's say theta equals 330 degrees. Theta equals 330 degrees. So let's draw our coordinate plane, and you may want color pencils as you're doing this at home so you can kind of see what I'm seeing here. We're going 330 degrees, which this right here is 270, and then that would be 60 more degrees. So that's going to be right there. So this is our theta equals 330 degrees. Okay, so drop your perpendicular from your anonymous point here. We don't know what it is. And what we want to find is our reference angle alpha there. We found our reference triangle. That would be our reference triangle there. So, but we need to find our reference angle alpha. Well, think about this. We don't know what this angle is right here. Okay, we don't know that. But we do know the red line angle here, angle theta, and we know the distance all the way around the circle, which is 360 degrees. So what we can say is 360 minus 330, and that gives us a reference angle of 30 degrees. So I know alpha here is going to be 30 degrees. So how would this work into what we're going to do? Well, when you get ready to look at this reference triangle, I know that this is going to be 30 and this is going to be 60. Now, why is that important? Because when I get ready to use the reference triangle we had on the previous screen, what I can do is I know that my hypotenuse will be 2. I know that my short side is going to be what? Short side is going to be 1. Long side is going to be the square root of 3. And you'll see how we're going to use that here in a little while. This is why you have to find the reference angle, so you can know where to put the 30 degrees, where to put the 60 degrees. It's not really going to matter where you put the 45 degrees, as you'll see in a minute, but where to put the 45 degrees, okay? This allows you to be able to see which way you are arranging your reference triangles, basically, which way it's flipped. It helps you from having to think about that, okay? It allows you just to go out and do it. So let's look at another one. Let's look at this one. Let's see here. Let's let our angle theta. Let's let angle theta equal negative 315 degrees. Angle theta equals negative 315 degrees. Well, Um, here we go. We have our coordinate plane. And so when you get ready to draw negative 315, that's going to start here. This is negative 180, negative 270, and negative 270 plus another negative 45 will give us a negative 315. So this angle right here is the one we're looking for. So our reference triangle, we have some anonymous point P. We're going to drop our perpendicular. And so this is going to be 45. This is going to be 45. Okay? Now, how did I know that was the reference angle? I got a little ahead of myself there. Well, I knew from memory, but let me show you how to get this. This is negative 3. This is theta equals negative 315, correct? Okay. So, how are we going to find our angle alpha? Well, we know, again, that the whole thing is 360. Okay? So if we subtract 315 from it, because remember, this angle here always has to be in the positive form. So that's why you notice we're subtracting that 315 from it, even though it has a minus sign there. Okay? And that, excuse me, even though we have a negative sign. It's still, you got to think of it in terms of the space it's eating up. It's eating up 315 degrees of our 360 degree circle. So how many degrees are left? Well, obviously, if it's eating up, whether it's positive or negative, if it's eating up 315, obviously 45 are going to be left over. So that's how I knew that angle alpha was 45 degrees there. Okay? That's how I knew that angle alpha was 45 degrees. Okay? So, with these reference triangles, well, let's not get ahead of ourselves. Let's try another one. Let's let theta, let's keep this in radian form. Negative pi over 4. Negative pi over 4. So, now, this is the great thing about one like this. Because I'm starting from the x-axis here, and I'm going negative pi over 4, which is the negative 45 degrees, basically. Okay? So that's my negative pi over 4 right there. This is theta. Okay? This would be theta. Now, notice what happens. The definition states, the definition of a reference triangle states, we take this here from this point and we drop our perpendicular to the horizontal axis. Uh-oh, Mr. Francis. This is supposed to be alpha. This is supposed to be alpha here. Well, they're one and the same in this instance. Now, obviously, alpha is always positive. So in this instance, when we have a negative angle like that, when we have a negative angle that gives us, that's in the same position as alpha, what we need to do is just take the absolute value of it. So alpha is pi over 4. Okay? The way you want to think of it in terms of distance. Space that's eating up. We're eating up negative pi over 4. We're going negative pi over 4, but we're still eating up the space of pi over 4. okay? That's how we get that positive angle, is what space are we eating up, okay? So they're essentially, our theta and alpha are the same. We just have to take the absolute value of the theta in order to keep our alpha positive. Alpha will always be positive. Okay? Let's try one more. And then we'll progress instead of digress. Alright, so let's let theta equal 4 pi over 3. And I know what you're thinking. Mr. Francis, 4 pi over 3 is on that chart. I know. It's on the unit circle, but we're still going to look at the reference triangle of it. So, here's our coordinate plane. So, we're going in the positive direction this time, so everything should kind of look normal for us. So, remember, 180 is pi, or 3 pi over 3. So, this would be 3 pi over 3. So 4 pi over 3 is another pi over 3 down. Okay, so it's going to be another pi over 3 down. So 4 pi over 3 is right here. Another pi over 3 down. Now, get ready to draw your reference triangle. Remember, we start from some anonymous point P. Sometimes you'll be given that point, but anonymous point P. And we draw our reference triangle. So we're trying to find alpha there. This right here would be our theta. Okay? Now, here's the deal with this. We went past the horizontal with 4 pi over 3. But notice, alpha is in between our line and the horizontal here. So here's how we're going to have to do this to find this distance. Our goal is to find this angle right in here, this alpha. So since 4 pi over 3 is past it, we're going to take 4 pi over 3 and we're going to subtract 180, or pi since we're in radians, from it. Because we know this distance. This distance is pi. This distance here, the distance from here around to here, is 4 pi over 3. So in order to find this shorter distance, what we're actually looking for, in order to find this distance here, we're just concerned about this angle right here. So in order to find that distance, we need to subtract 4 pi over 3 minus the distance we know of pi to get that angle. Alright, so that's going to be 4 pi over 3 minus 3 pi over 3. Once you get your common denominator, and that is going to give you pi over 3. Okay, so alpha in this case would be pi over 3. Alpha in this case would be pi over 3. Alright, so that's how to actually find your reference triangle, how to find alpha. Those are going to be 2 key things for you to help determine basically what alpha, the sole purpose of alpha is to help you determine which way to flip your reference triangle, like I said earlier. Okay, so keep that in mind. Now what we're going to do is we are going to use this to sometimes find P. Okay, we can use it to find P. And we can also use it to find the 6 trig functions. The 6 trig functions. So in order to compute that, now note, here's a little note for you. When we flip our reference triangle, okay, like when this one here, this reference triangle that we have right here, pi over 3 is the same thing as 60, so I know this is 60 degrees here, this is 30 degrees. So based on our reference triangle, I know this has the square root of 3, this has 1, this has 2. Now, that's just the way we flipped the reference triangle from earlier. Now, here's the part you got to be careful with. You've got to be careful because you can't forget your sine. This is quadrant 3 is where this angle is. Both values are negative in quadrant 3. So this is going to be a negative 1 and a negative square root of 3. Okay? When you begin to use your calculations, you have to use the negatives. Okay? You'll see more about that here in just a minute. So depending on what quadrant is in, these signs can change on the legs here of your triangle. Now here's the deal about this. We actually know what this angle, this point P right here is. This point P is negative 1, negative square root of 3. This is our y coordinate. This is our x coordinate. Okay, think of it in terms of distance. So you can see you can actually find point P with these reference triangles. So it's going to allow you to find sine, cosine, and tangent as well. Because sine, cosine, and tangent will sine, cosine, and tangent will can be found very easily from these. But the hypotenuse is what we've got to worry about. Now, if this is a perfect triangle, we're really it's not really gonna matter. But remember, if we need to find the hypotenuse, suppose you don't know the hypotenuse here, then suppose you're just given the point, so to speak. Suppose we're just given our A and our B, and we don't know what the hypotenuse is. Remember, the hypotenuse of this triangle is the same thing as the radius at point P. Well, what if we don't know what that radius is? Now, we do with these reference triangles, fortunately. Fortunately, we know what those are. But what if we don't? Well, remember what radius equals. Radius equals the square root of a squared plus b squared. So even if we just know the point P, if I just gave you some random numbers for point P, you could find the radius and find sine, cosine, and tangent very easily after finding the radius, because here's why. Remember what sine, cosine, tangent equals. A, and B over A, respectively. But in terms of these angles, sometimes it's better, instead of using A, B, and R, sometimes you're going to see it interpreted with words like hypotenuse, opposite, and adjacent. So earlier, we defined it as this. We said sine theta is B over R. We said cosine theta is A over R, and that tangent theta would equal B over A. Now, sometimes it may be difficult to interpret it as A, B, and R. Sometimes it may be better for you to interpret it like this. Sine is the same thing as the opposite leg over the hypotenuse. The radius is always the hypotenuse, remember. So the cosine would be the adjacent leg over the hypotenuse. And tangent would be, of course, the opposite over the adjacent. Opposite over the adjacent. Now, we had a saying for this when I took trig. If you took trig in high school, your teacher probably taught it to you too. Oscar had a heap of apples. That's how you can remember that. Oscar had a heap of apples. Now, to get secant, cosecant, and cotangent, obviously, you just do the reciprocal of sine, cosine, and tangent. Okay? Of sine, cosine, and tangent. Alright, so we will do some examples on our next video.